Welcome to this learning video about the method of Lagrange multipliers. I will explain this method using a concrete example. Consider a very simple function which is in this case x times y, and we want to find the minimum or the maximum of this function subject to a certain constraint. And our constraint here is x squared divided by a squared plus y squared divided by b squared is equal to 1, where the a and b are given as constants greater than 0. This constraint here is an ellipse. It is the equation of the ellipse with given semi-axis a and b. So let me make a sketch. So here you see the semi-axis a and b, minus a, minus b. So we are looking for points on this surface f of x, y, which is defined everywhere, which you can imagine as a landscape over the xy plane that have the minimum or maximum function value, but only those points that lie exactly on the red ellipse. You can think of it like cutting out a cookie from this landscape and then focusing on the edge of that cookie to find where the function reaches its maximum or minimum. This problem can be solved using the method of Lagrange multipliers, which I will now write down in general terms. So in general, we have a function, an n-dimensional function, which has to be minimized or maximized, and there are given constraints. In general, we don't only have one, we have m constraints. So it goes down to gm. And we say these are equations in the form that they equal to 0. So n is the dimension of the axis and m the number of constraints. So then the general theory says we have to set up a so-called Lagrangian function or some people just say Lagrangian instead. So what is that? It is a function L depending on all the n variables. And in addition, this function depends on the m parameters for the constraints. So lambda 1 up to lambda m. And how is it defined? It is defined as the function itself. So f of x1 up to xn. But that's not all. The function itself plus the introduced parameters lambda 1 times the first constraint equation, depending on x1 to xn, plus up to lambda m, the last constraint equation. So you will see later why this works. So the general theory says compute the partial derivatives of this Lagrangian according to all the variables starting from x1 down to xn, And also you need then the partial derivatives according to the new parameters lambda 1 down to lambda m. So the first partial derivatives are set equal to 0. This is how you get a minimum or a maximum of a function. But if you compute the partial derivative of the Lagrangian according to the variable lambda 1, you see there is no lambda 1 in f, and the derivative of lambda 1 is 1. So what remains is just g1 of x1 up to xn. And you also set this to 0. So this means we fulfill our given constraint, which actually was given automatically now. And the same here for all the others. So the Lagrangian differentiated according to lambda m is then gm from x1 to xn, and this is also set to 0. So now let's go back to our specific example. The function depends only on x, y, on two variables. So the small n in this case is equal to 2. We have one constraint, which means the small m is 1, which is the equation of the ellipse here. We just need to rearrange it by bringing the 1 of the equation of the ellipse to the left-hand side so that it is equal to 0. This means our Lagrangian function L depends on x, y. So probably on x, y. And in addition, on only one parameter lambda. And the Lagrangian is the function itself, x times y, plus lambda times the constraint. So the equation of the ellipse but equated to 0, so minus 1 here. So next step, compute the partial derivatives. So partial derivative of the Lagrangian with respect to the variable x first. So if you derive according to x, it just is y plus lambda, and inside here it is 2x divided by a squared, and this should be set to 0. Next one is x here plus y, but now we have instead 2y divided by b squared if you derive it by using the power rule. So 2y divided by b squared, nothing else contains a y value. And we also need the third partial derivative according to the introduced parameter lambda. In this case is just the equation of the ellipse. And we also set it to 0. So the derivative with respect to the lambda always gives the constraint function. So we have set the partial derivatives equal to 0 and solved now for x and y from these equations. The parameter lambda is essentially an auxiliary variable called also the Lagrangian multiplier. Let's write it here probably. So Lagrangian multiplier. And this is important, and we cannot simply ignore this parameter here. So usually we express lambda from one equation and substitute it into the others. So this means here from the first equation, you can express the lambda very easily, which is now minus y a squared divided by 2x. So minus y times a squared divided by 2x. Similarly, you do the same here, which is minus x times b squared divided by 2y. So you have two equations for y, and this means we can now substitute these two equations and get an equation without this auxiliary variable lambda. So I can neglect the minus, I think. So y a squared divided by 2x is equal x b squared divided by 2y. The 2 cancels out. So we express one variable, for instance the y. So you move this y also to the left side here, so we have altogether y squared is equal, the x to the right side is x squared b squared divided by a squared. So we do not take the square root here, as we use it directly now in the constraint equation. This y squared appears also here in the constraint equation here. So what is the final formula? Where should I write it here? I'm running out of space again as usual. So x squared divided by a squared. This is my constraint equation. Plus, instead of the y squared, I plug it in here. So I have 1 over b squared to the front. X squared b squared divided by a squared is equal to 1. So I again move the 1 to the right side. So what cancels out is the b squared here, and the whole equation simplifies to 2 times x squared over a squared is equal to 1. And from this, you simply can compute what is the x value. So the x is then plus minus a divided by the square root of 2. Don't forget the plus minus here. And what does this mean now for the y? Let me use the fancy color, and it is a bit messy here now. So for the y squared, you can use the x squared from below. So it is then a squared b squared divided by 2a squared. Should be fine, because x squared is a squared divided by 2. So we have a squared b squared divided by 2a squared. And you simply get here now the values for y, which is again plus minus. Simplify the a squared again. B divided by the root of 2. So altogether we have 4 solutions of this nonlinear system of equations. So if you look here, this is far away from a linear system. It's a nonlinear system of equations. And the 4 solutions I write here below this elliptic plot. So first one is if you take a plus to both. Second one plus minus. Third one, minus plus. And the fourth one, minus minus. Here I should write the minus. So if I sketch these, they are approximately here. So here is x1. Then the next one is here. This is x3. Here we have x4. And here the x2. So x is positive and y is negative. Fine. So now we have found 4 candidate points for the minimum and maximum of the functions, which are illustrated here. From the problem setup, it's clear that since we are restricting ourselves to a closed curve, the ellipse, there must be at least one maximum and one minimum. However, the Lagrange multiplier method doesn't allow us to determine whether a critical point is a minimum or a maximum using the second derivatives. Instead, we must rely on symmetry or compute the function values directly, which we're gonna do now. So we calculate the function values at the 4 candidate points. As f of xy is x times y, what are my function values now? So the f1 is then simply a times b over 2. The function value for f2, for the x2 I mean, is minus ab over 2. f3 is also with minus ab over 2. f4 is ab by 2. So now it's easy to classify the points. The point in the first quadrant here is a maximum. The 2 points in the second and in the fourth quadrant, so x2 and x3, they are minima. And the point in the third quadrant is again a maximum. Thus, we have found 2 maxima and 2 minima, alternating as we move along the curve. So here, positive, negative, positive, negative. That's all I wanted to tell you about the Lagrange multiplier method. Thanks for your attention and see you next time.